Okay, let's see if I've got everything. I was looking for sound too. I have to admit this is a very difficult talk to write. Essentially, writing the talk made me reevaluate my entire career, and it was also quite sad. Anyway, I'm ready to start. Okay. So 20 years ago today, I took this picture of him in his office in the University of Pennsylvania psychology building, which is probably the ugliest building in all of the Union campus. It really looked like a concentration block on the Soviet joke. So this picture, which is kind of iconic in that it ended up being in a lot of his subsequent web pages, I took on a whim because he had this ridiculous hat. And then he made the rest of us in the lab at the time, which was me and this other woman named Crystal, who, if you're here, stand forward, but otherwise, she was only in the lab for a year, and I forgot even her last name. But both of us took these pictures with the hat, and that was our lab pictures at the time. So I met him in 1994 when he first came. I was working with David Knill at the time, Eros Micheli at the time, and I was very much in a reductionist neuroscience mode. And Dave came along and kind of broadened my horizons, and in many of the ways introduced me to the things that Dave Kirsten just talked about. And by the time that I finished, I really felt like Dave had become kind of an iconic figure because of the publication of Perception as Bayesian Inference. And he also ended up being really, I think, identified throughout his career as part of the Bayesian brain movement, which in a nutshell is that ecological perception is complex and ambiguous, as Dan pointed out, and that ambiguity generates uncertainty, which must be handled well to guide actions. And this is the evolution of man to Homo Bayesianus, at the bottom, giving the posterior right. So where I started was really down at this level here. I came out of undergrad with a neuroscience emphasis, physical chemistry, mathematics, and I really felt like I would understand things best if I went to the lowest possible level of the brain. And when I met Dave, I suddenly got introduced to the very highest level of Mars analysis. Most of you probably know Mars analysis. But Dave basically did his entire career here at the computational level, asking questions: why do things work the way they do? What's the goal of the system? What are unifying principles? And one of the most profound things in my graduate career was really getting introduced to this illusion, because I had been introduced to the mechanistic explanation in a book. I think it's the Tom Cornsweet book, but I don't remember exactly. But so this was really a whole strategy of explaining perceptual illusions as byproducts of really sensory processing, and it's very mechanistic. And then along came what I'm going to call today computational epistemology. It's a way of thinking about how we come to know things from a computational point of view by working in the realm of causes. And it really introduced a new framework for thinking about illusions, in which illusions are stemming from a rational analysis of a scene. That illusions are not stupidities in the brain, they're actually revealing our intelligent processes. And that actually took quite a hold of me. And it's sort of strange now to see the backlash in some ways against Bayesian approaches. So here's a recent quote that I picked from a journal where the emphasis on the new tools that are available to neuroscientists is really leading to causal systems analysis at the neural level, meaning that we may not need Mars analysis anymore. And if I can get this to work, I thought Dave might appreciate this.
However, we scientists have now located a gene which we scientists believe gives people the need to believe in God. In other words, this God gene releases chemicals into our body which create the impression that there is meaning in the universe. And this God gene is just here, between the gene which we scientists now know makes us eat coconut ice cream after fish dinner, and this gene here, which causes people with weak egos to grasp around desperately for simple explanation. The discovery of this God gene is a big step forward in our quest to show that every bit of human behavior can be explained away mechanically, because we've now also located the gene which makes some people believe that every piece of human behavior can be explained mechanically. And it's here, right next to the gene that makes you go to see Nicolas Cage movies, so and right under this gene, which can cause you to forget that since the 1920s, quantum physics has destroyed forever the idea that everything can be explained mechanically.
So that's my take on mechanistic explanation. So I'm actually going to skip now to a set of slides that are actually Dave's. So we're now looking at a bit of history from when Dave gave a talk at a symposium at VSS that Peter Vitale and I organized in 1998, or 2008, sorry. Yeah. So, and in this, he's really trying to describe a framework that I think constitutes his research program post-Dan and leading into pretty much the rest of his career. And it's he was looking for a rational analysis approach to vision, grounding it. And so here's his explanation of what a good computational level framework looks like. And it should support building predictive models of perceptual performance. It should support bridging statements between models and descriptions of behavior. It should explain why perception and sensory motor control works the way it does. And this why question is really integral to almost all of the discussions that Dave, Knill, and I had. It's this insistence on the why that has infected me, and I don't think I've ever been the same. And a good framework should also help guide psychophysical research. It suggests new and interesting theoretical questions, and so on and so forth. And so here's Dave's slightly later version of Dan's forward graphics version of computational vision. But we have a world model here, and a world model warrants a description in its own right. And we have the traditional encoding of what's in the world in a generative model of images. So here's the Dave's very explicit recognition that the generative models that have been used in most of Bayesian approaches to vision were essentially models of this encoding process with some issue with the prior. And then you need a way of talking about how the brain extracts from the sensory messages through a rational inference process estimates back of the things that it needs. And the things that are new in this are down here, this task model, which turns out to be very important in Dave's later thinking. And this reconceptualization of an ideal observer as a glue, which pulls together a generative model of the world, a generative model of the encoding of the world into sensation, and actually a generative model for tasks. So these are the natural behaviors that people would execute. And so where Dave, and these are all his slides, where Dave was sitting is an ideal observer model helps generate hypotheses that allow you to conduct a rational analysis. And from a rational analysis, you get then an interesting description of sensory motor perceptual behavior. And so the domain of Bayesian models is this bridging. It's being able to create an interesting causal language description. And I'm going to skip this because Dan talked about some of that. and move on to what he was working on when I was his graduate student. And one of the funny things is that I basically carried in a project into his lab that had nothing to do with his main line of research. And I basically borrowed methodology to work on motion processing, watching him do the work on the problem I'm going to describe right now. And that's trying to understand, again, this problem of how we estimate surface normals. But now he's abstracted it to a single planar surface and looked at the role of texture. And getting at the role of texture at the time that he was working was pretty tough. And he basically designed a really interesting ideal observer analysis. So an ideal observer analysis is meant to describe how well any observer can compute surface orientation from texture. And so if I give you this family of textures, you would like to have a procedure that can really take this image data and produce a slant. And all of you are probably seeing slants in these different scenes. The question is, what are you doing? And one of the distinctive things that I learned from Dave was to focus on knowledge. So what knowledge does the brain need in order to solve this problem? And by focusing on the knowledge, it's really the causal knowledge that you need. Then you can boil down this process into one in which you can design an observer that can actually do the same task as people, and thereby have a description, a functional level description of the task. One really key component was the geometric knowledge. The geometric knowledge is essentially perspective projection, but you have perspective projection operating on these very chaotic image descriptions. Textures are not all just one thing. They're not that easy to describe. And they come with them their own description in the world, a statistical description that requires you to know something about the regularities of the world. This is a very particular kind of regularity. Dan was talking about regularities in the world that have to do with object shape and surface. Here we have regularities in textures. And the really critical regularities in textures in order for you to interpret them as slants are these two things here, homogeneity and isotropy. Homogeneity means that everywhere you look in space, the texture has similar statistical properties. And isotropy means that there isn't any preferred orientation. However, it turns out that neither one of these assumptions are really necessary, and people really can see slants from texture when both of these assumptions are violated, and Dave actually knew this. So here's an homogeneous textures, and here's a texture that is anisotropic. So one of the first things he did was to systematically define cues. And this itself was an appeal to the tradition and vision of trying to think about something like slant as a combination of simple cues out in the world. Now, what is a cue when you have texture? And that in itself had to be defined. And Dave did this by working through the mathematics that he had learned about geometry in order to define these distortions, and discovered that almost all of the traditional cues for texture that had already been described corresponded to deformations in elements that are just ellipsoids. So if you fit an ellipsoid to a bit of a textured patch, and when you look at how that region distorts, then you end up with a fairly simple set of three parameters. You take those three parameters per element, and then you stretch them over space, and you look at the spatial pattern that results in these three parameters, and voila, you get all of the cues that people have been talking about. And you get ways to manipulate these cues in images. And he ended up having a very clever, highly technical way of generating the textures that you were observing through a reaction diffusion process, blah, blah, blah. But one of I think the really interesting things that came out of this definition of cues and textures is he was able to do an ideal observer analysis by defining observers that could use the information absolutely the best. And when he did that, he compared the slant estimates that an ideal observer would get against a human observer. Lo and behold, people suck. And this is, people have often thought that being Bayesian means that you think people are near optimal. And it actually has never meant that. We've always known that people are massively suboptimal relative to ideals. The much more interesting thing is how you use ideal observer analysis in order to quantify what information is available and what information people are using. And so you can begin to ask the questions like, why are people so bad? And what Dave did was he did a manipulation in which he changed the width of the viewing region, so to offer less information. And then he found that people's efficiencies, thresholds, were relatively flat. And what this means in a nutshell is if I give you less information, you perform the same. You didn't need this extra information. You weren't able to use it. So people are just inefficient. They're just looking at tiny patches of the scene. So that's a huge bit of why they're inefficient, but maybe not all of it. The other thing that Dave did in this early set of papers in the 90s is he did really the first reverse correlation after Al-Ahmada's sort of landmark reverse correlation analysis of frequencies in audition. And it was right after Jenny Richards, who was a co-faculty with us at Penn, had done a reverse correlation analysis, again in audition. So what Dave realized is that when he's introducing these stimuli, he had a random process for generating the stimuli. And that means that the cues on each one of these stimuli had a slightly different value. So these cues are fluctuating. All of these are being passed through some function in order to estimate slant, and you're getting a slightly different slant value on each trial in terms of their judgments. So now you can take the Q values, the people's estimated slant values, and lo and behold, you have a really nice way of generating an elicitation procedure where you can identify people's strategies. When he did that, which became really common throughout the 90s and 2000s and still being used, you can get Q weights then basically automatically through a rational analysis. So the Q weights that he found ended up showing that the position had no influence. Position is the Q in which the elements are more tightly packed together in spacing near the horizon. So people don't use that at all. Scaling is the cue that the ellipsoids are smaller along the horizon. People use that somewhat. And then foreshortening is the cue that the ellipsoids change direction to be aligned. They're all basically aligned here. They can be any direction near the boundary, but the orientations come together, and also the aspect ratios systematically change. So this cue was dominant, except for textures that had higher order moments than ellipsoids, like rectangles. And the other thing that Dave was able to show in this really early analysis is that people don't stick with one strategy. They actually change strategy as the environmental regularities change. So he introduced systematic violations of isotropy and discovered that people's reliance on the foreshortening changed exactly how you might expect. And he was able to define not only an ideal observer that assumes isotropy, but he was able to define a family of ideal observers that make use of different statistical regularities in the environment. So if isotropy is true, you can use it. If it's not true, you don't. And he also gave a compelling Bayesian analysis that we may hear about later that shows that your brain can actually pick up on the information it needs to test these assumptions and adapt automatically. So the last thing I would like to tell you about is, again, this probing nature of his questions. He was really asking in most of these studies, what are Qs? What are Q weights? So this is back to his talk in 2008. He's asking, what are the nature of Qs? Are they summary descriptions? Are they information available to the task? Are they this logical links between behavior and rational normative model of performance? And essentially, that's he came down again and again that the analyses that we're doing are basically giving us a handle on the causal assumptions that people are making about the world. So when we make statements like humans weigh century cues optimally, it's really not that meaningful, because what we usually mean is something like a linear process model in which we get data, we weigh it deterministically according to weights, and we make an action or decision. And there's plenty of papers that support this view, but that's not the view that Dave ever took. Instead, he took the view that cues are simply our operationalization of the operations on the image that people need to do to extract the information that they need. And moreover, that the information that they need, for instance, to depth or slant or any of these other variables, are ultimately determined by the family of tasks that we do. So he became increasingly interested in specifying a set of natural tasks that lead to not only what cues, but which variables do we try to integrate over. And did experiments like this, where he tested whether or not we process depth differently, this slant, exact same slant task, but now if I reach and I move a Coke can and place it on an oriented surface, do I use the information the same between stereo and texture as if I'm doing a judgment? And he found systematically the answer is no. In a motor task, we use these cues differently, supporting these notions that we may use visual processing quite differently to subserve our different needs. And I should probably wrap up. So the main lesson that I learned from Dave working with him is that theory matters. And it's not a theory of vision unless it can handle real stimuli and tasks. He basically did functional analyses where the why and the what comes before how. Not that he wasn't interested in how, but if you don't get this right, you won't be able to get the how right. And you develop whatever theory you need along the way. The other thing that Dave taught me is how to design airtight psychophysical experiments. But you embed these experiments in near ecological context. And increasingly throughout my career, I've violated this somewhat, but it's painful to me to do so. Personally, the one personal reflection I'd really like to share is that he taught me how to concoct a story on the spot. And I don't know if any of you were here when late one night on the beach at VSS in the 90s, he had a whole group of people convinced that there was a Chinese influence on the origins of Appalachian folk music. And he did this for about 10 minutes with a straight face, kept going until somebody finally said, "Really?" And they said, "No." That's all.
If you have questions for Paul, quick ones, we can take one or two, or if you have reflections about Dave that you'd like to share in light of Paul's presentation, that would be great as well.